In this lesson, we're going to talk about how to solve single variable inequalities. To solve single variable linear inequalities, we're going to use the properties of inequality to solve linear inequalities and determine which case applies. So the properties of inequality are the same properties as linear equalities. That is the addition property of equality and the multiplication property. In case 1, we have one solution, and what that really means for inequalities is we have a range of solutions. In case 2, there will be no solution. That means there's no real number possible for x to equal to make a true statement. And finally, in case 3, there could be an infinite number of solutions. To solve linear inequalities, we're going to find that there are a variety of ways to display our final answers. So we are going to work through the inequality to solve it, and when we get x compared to some number, that is going to be the algebraic notation automatically. From there, I'll show you how to graph your answer on a number line, how to write the interval notation, and finally how to use the set builder notation to display our answer. So in example 1, we have 0.7x minus x is greater than 0.45. So we notice right away there are decimals involved, but it will be pretty straightforward to work with the decimals. One thing to point out is when working with these decimals, be very careful when you're combining like terms. You notice these first two terms are like terms, but we have subtraction of x. You may want to rewrite that as 0.7x minus 1x is greater than 0.45. This way it's easy to see what the actual coefficient of x is, because when we don't see anything, sometimes people forget that it's really 1. In this case, it is -1 because the problem is written as subtraction. So what we're really combining is 0.7 subtract 1, and that will give us a negative 0.3x is greater than 0.45. So you can see that the variable is already collected on the left and our constant term on the right. However, x does not have a lead coefficient of +1. So this multiplication of -0.3 will need to be eliminated by dividing both sides of this inequality by -0.3. Now right away this brings us into one of the important rules we're going to need to know about inequalities. When you divide by a negative number or multiply by a negative number, that will reverse the inequality symbol. So now that we're familiar with that rule, we're going to automatically change that inequality now to less than. We can reduce, and we have x is less than +0.45 divided by a -0.3 is -1.5. So this is our algebraic notation. I'll just rewrite it over here. X is less than -1.5. Now from here, we should be able to display that on a number line. On the number line, I'm only marking where -1.5 appears. So I'm just going to pick some place near the middle, -1.5. To be less than that is shading to the left. We do not have equal to -1.5, so we use a parenthesis at the -1.5 to show that that value is not included. For the interval notation, we are describing where all of the shading is. Remember that an arrow indicates that the shading goes forever in that direction. So if your shading goes to the left, it's really going to -infinity. If your shading goes to the right, that would be going to +infinity. So our shading heads to the left. That means our interval is -infinity, comma, -1.5. And since negative 1.5 is not included, that will also be a parenthesis. If our problem originally has an equal included, we would use a bracket at that number, but we'll have an example of that coming up. Finally, the set builder notation involves these set brackets, which can be difficult to draw sometimes. Our variable is x. So right now this says the set of x such that, and then we simply write our algebraic notation. So the set of x such that x is less than negative 1.5, and close the set brackets. Now we are assuming that x comes from the real number system. So what's important to remember from this example is when you multiply or divide by something negative, it will reverse the inequality symbol. For example 2, you'll notice that we have some parentheses, so we're going to need to distribute to figure out what all of our terms are. We've got 3x plus 1 is less than 3x minus 6. So I like to collect the variables on the left side of the inequality because that will make the graphing and interval notation easier to interpret. So I will subtract 3x from each side of this inequality. It eliminates on the right side. Notice it also eliminates from the left. I'm left with 1 is less than negative 6. Is 1 less than negative 6? No. So when you end up with a false statement, notice we don't have a variable remaining, so there's no way to write the algebraic notation. There isn't any. For the graph, if there are no solutions, you can draw the number line but shade nothing. The interval doesn't exist because there are no solutions, and the set builder doesn't exist. So really the only thing we can determine here is that there are no solutions, therefore the graph is remaining empty. For example 3, again we have parentheses, so let's distribute the 4 to each term in the quantity. 4x minus 4 is greater or equal to 4x minus 8. Collecting my variables on the left side, I will subtract 4x. So 4x minus 4x eliminates on the right, and it eliminates on the left side of the inequality. I have negative 4 is greater or equal to negative 8. Is negative 4 greater or equal to negative 8? Well, we know it's not equal to. And on a number line, just think about where these numbers would occur. If that's negative 4, 0's over here to the right. Negative 8 is going to be to the left. The farther away from 0 on the left, the smaller the number. So negative 4 really is larger. This time we end up with something that's true. That tells us that no matter what value for x we use, it will work. So all real numbers will work. So we do not have an algebraic notation to write for that, but the graph, where are all the real numbers? They're everywhere on the number line. So this time the entire number line is shaded. And that interval includes negative infinity to positive infinity. And those are the only two types of notation we would use to write our answer. So this is another special case situation. Notice here in example 4, we have some fractions. So we're going to have to go back and think about lowest common denominator to help us eliminate the fractions from the inequality. One of our denominators is 7. So if I divide 7 by prime, 7 is the only number that it's divisible by. The other denominator is 4. Dividing 4 by 2, I get 2. Divide 2 by 2, I get 1. So the factors involved here are 7 and 2. So the highest power of 7 is 7 to the power of 1, so I have enough. But notice here 2 is written twice, so that's the same as 2 squared. So I need the highest power of 2. 7 multiplied by 2 squared is 7 times 4. That makes 28. So I use 28 to multiply all terms in the inequality. So I'll have 28 times my fraction 5x plus 1 divided by 7 minus 28 times our fraction 2x minus 6 over 4 greater or equal to 28 times negative 4. So what happens here, remember 28 can be written as 28 over 1 when you have that written next to a fraction. So the reducing that I can do here, 28 sevenths makes 4. And here, negative 28 fourths will make negative 7. 4 will be distributed, and that gives us 20x plus 4. For the next distribution, remember it's a negative 7 that I am distributing to each term in the quantity. So that would make negative 14x, and a negative 7 times a negative 6 would be positive 42. And that's typically where the mistake occurs. So do be careful with that negative 7. And that would be greater or equal to 28 times negative 4. So I know I'm going to have a negative product here. So 8 times 4 makes 32. And 4 times 2 is 8, 9, 10, 11. So negative 112. If there are any like terms here on the left, we want to collect those before we start moving anything across that inequality symbol. So it looks like I've got a couple of like terms with x, and I have some constant terms that are like terms. 20 take away 14 would give us 6x, and then that gives me 4 added to 42, so that would be positive 46, greater or equal to negative 112. 6x is the only variable term, so I'm leaving that alone and subtracting 46 from each side. So if we eliminate it from one side and collect it on the other, we've got 6x is greater or equal to, and since both of these numbers are negative, we simply add them and include the negative. Yeah, that looks like 158. So our final step now is to get x isolated by dividing by 6. Since 6 is a positive number, we keep the greater or equal. Do not reverse that symbol. So we have a negative divided by a positive, so we will have a negative answer here. Now I notice that both 158 and 6 are even numbers, so they are both divisible by 2. So with the reducing, if I divide each by 2, I'll have, what, 78? No, 79. So that's as far as I'm going to be able to reduce that, leaving it as a fraction. And you could convert it to a decimal if you want to. So this is the algebraic notation. X has to be greater or equal to negative 79 thirds. On the number line, simply pick a spot, call it negative 79 thirds, and we need shading greater than, so shading to the right. Equal to means we're using a bracket. So the interval would be bracket negative 79 thirds all the way to positive infinity with a parenthesis. So remember, whether it's negative or positive infinity, we're always using a parenthesis. I use a bracket for this number portion if an equal sign is included in the inequality. Finally, the set builder notation, our variable is x, so we want the set of x such that x is greater or equal to negative 79 thirds. So if you have fractions in the inequality, you approach it just like equations. Find the LCD, multiply all terms by it, and once you reduce, the fraction should be eliminated. We do have another example with fractions here, and these fractions, we've got 4 different ones, and all of the denominators are different. So we're going to have to do a little bit of work here to come up with our lowest common denominator. Starting with 12, if I divide by 2, I get 6. I can divide again by 2 to get 3. Dividing by 3, I get 1. So the factors or prime factors of 12 would be 2 squared times 3. Then I've got 3 in another denominator. So 3, you can see, is already prime. Next we have 8. 8 is divisible by 2, leaving us 4. 4 is divisible by 2, leaving 2. 2 is divisible by 2, leaving 1. So 2 times 2 times 2 would be 2 cubed. Finally, we've got 6 in a denominator. I could divide by 2 to get 3, divide by 3 to get 1. So the factors are 2 times 3. So it looks like all of our factors involve either 2 or 3. So I'll start with 2 multiplied by 3. Now I need to check what power they are raised to. So I'm going to check out all of our 2's. 2 squared, there's no 2. 2 cubed, and 2. So it looks like 2 cubed is the highest power of 2. So I need to include the highest power of 2. Now we'll compare all our factors of 3. 3 to the first power, 3 to the first power, 3 to the first power. All of them are 3 to the first power. So 2 times 2 times 2 makes 8 times 3, which is 24. So I need to multiply every term in the inequality by 24. So I'll have 24 times 7/12 x minus 24 times 1/3 less or equal to 24 times 3/8 x minus 24 times 5/6. So I should be able to do some reducing and eliminate all of our fractions. 24/12 is exactly 2. 24/3, remember it's a negative 24/3, that's minus 8. 24/8 would be 3. And negative 24/6 would be negative 4. So now I can clearly see in red what needs to be distributed. 2 times 7x would be 14x. Negative 8 times 1 is negative 8, less or equal. 3 times 3x would be 9x. And finally, negative 4 times 5 would make negative 20. So we do not have any fractions remaining. That's good news. It means we did use the correct lowest common denominator to help us eliminate our fractions. So it looks like we're ready to collect all our variables on the left side of the inequality. I'll subtract 9x from each side. So it's eliminated from the right side, and it looks like 5x minus 8 is less or equal to negative 20. And adding 8 to both sides of the inequality results in 5x less or equal to negative 12. So all we have to do now is divide each side by 5, and because it's positive 5, I do keep the less or equal to symbol. So x is less or equal to negative 12/5. This is our algebraic notation. And we're ready to go to the number line to graph this solution, or a whole range of solutions, really. So I'll pick a mark, call it negative 12/5. Less than would be to the left. Equal to means I need a bracket. So the interval notation is from negative infinity up into including the negative 12/5. So I do have a bracket. So notice I am just describing this shaded region. The set builder notation, the set of x such that x is less or equal to negative 12/5.